All right, welcome. Thanks for watching the video, coming here. We're going to do section 32 here, so let's dive into it. 32.5 is fusion. So the kind of backstory here, nuclear fusion is a reaction that in which two nuclei are combined or fused together. They form a larger nucleus, and then the mass of a nucleus is less than the sum of the mass of the particles that make it up. And that makes some energy in the E equals the change of mass C squared. That is the binding energy of the nucleus. So there's some energy that gets converted, some mass that gets converted from energy and then turns into just the binding energy, what holds that thing together. The binding energy per nucleon is usually listed as Be for binding energy, and then divided by A, which is the number of protons and neutrons added together, is greater for medium mass nuclei, and it maxes out at iron. So we can see here in this chart that I've got iron is, I don't know, one of these guys up here. It's the biggest one. I can't tell which one it is by this chart. But iron's hanging out there, and it's the highest amount. So, in fact, anything that is smaller molecularly or smaller atom than iron, you're going to get energy out of that by inducing fusion. Anything above that, it's actually going to cost energy in order to fuse. So if you came in, started a company, and you're like, we're going to come up here with tellurium and fuse it to get energy, that's going to be a waste of time because it's going to take more energy to get that to turn into the next element up, or anything higher than tellurium, and it'll not work out for you. Right? So these energy values along the side, these kind of this range here, this is the good range to do fusion, and then anything beyond iron is costly to perform fusion on. It's going to cost you energy, and so even in this little range here, you probably want to be dealing with as far to the left as we can get, because you can see the jumps here. There's a kind of a small jump between hydrogen and helium, but if you go from helium-3 to helium-4, there's a much larger jump there. And so we're trying to kind of target what we want to do. There are some even downslopes, I think, between oxygen and whatever's next after oxygen, the seventh or the whatever ninth element is a loss as well, due to just the makeup of their structures. But for the most part, trying to turn this into some controlled form of energy, we want to kind of stick with the maximum output for the minimum effort, which is kind of how everything goes. But the question now is, why doesn't this just happen all the time to, say, helium particles inside a balloon? Why don't they just fuse together and dump out all of this energy? So the Coulomb force, I think I have a picture. Yeah, sort of, yeah. Also, while I'm grabbing this, the program that I use will only allow me to do 30-minute videos, so this will probably end up being hopefully not three videos for what we're trying to do here. But on this top row here, you can see, well, on the left in A, we have two nuclei coming at each other. This guy right here, well, this guy right here is headed this way, and then this guy right here is headed this way. And as they get closer, we still have the Coulomb force. that says, nah, you guys take off, and they'll just kind of turn around and, all right, sorry, my bad, and they go the other way, right? But the energy that's required to get these two to come together, right? These two, if they want to come and actually be in physical contact, it takes a huge amount of energy, and we have to get these temperatures up to, don't do that. In fact, in order to get these two to touch, touch being close enough for the strong nuclear force to be appreciable and then to bring the two together, it takes temperatures on the order of 10 to the 8th Kelvin, which is ridiculously hot, right? It's hotter than the sun. It's hotter than the core of the sun, where this type of activity happens. And so there's something that is needed to explain this. It's not just temperature. You can't just get it hot enough, because we can't get it hot enough. It doesn't work to get these two to actually be close enough. And so what the explanation is there's something called quantum tunneling. And we're not going to talk much about it other than to just kind of say what it is. But quantum tunneling is, if you were to look at this maybe on a macroscopic scale, it would be like if I were trying to throw a ball over the Empire State Building. And here's me, and I'm like, hey, I'm going to make it. And it goes boink, and I'm not even close. And so there's this huge amount of energy that I have to overcome in order to get this ball. I could, get a cannon maybe and shoot it. But in the classical sense, the only way for me to get this ball over this is to impart it with such an enormous amount of energy that it can make it over that building. I alone can't do that, clearly. But if I could just be like, hey, you know what? I'm going to throw it at the building and see what happens. And it just kind of disappears and boop, pops right out. And that's why it's called tunneling, because it goes through these barriers without overcoming the barriers. It's quantum. The quantum world is crazy and funky, but this is one of the things that happens once we get down here. And the reason that this can happen is due to the wave nature of these particles. So the wave nature of matter makes this possible. Clearly, the bigger an item, if I threw a bowling ball at that building, it's just going to break the window, whatever. But we're talking about these teeny tiny little particles, and they are essentially just waves out there. And if they interact, they can just be like, go around the gate, go around the fence, whatever you want to look at it. But it doesn't have to overcome that barrier. It just tunnels right through it and says, sucks to be you, I'm out. And that's what happens. It still takes a lot of energy, right? So on the right-hand side of this picture here, what's happening is these two are now coming at each other with a very high temperature, and they get close. I don't know if you can see it there, but they're not actually touching. Yoink, yoink, yoink. There's some space between the two of them, and they don't actually have to touch. There's still a humongous amount of the Coulomb force that says, no, you guys can't come together. But then they tunnel, and they're like, nah, screw you. And they overcome that barrier without having the energy necessary to do so. They tunnel through the barrier. They become intertwined, and they are now fused together. In that process, there's typically a neutron is dumped out, and some photons, gamma rays, are also dumped out. So what happens depends on the reaction. There are a few reactions here in the book. I'll just steal and post here. I've got a hydrogen, a simple hydrogen, just a proton, slams into another proton, tunnels into another proton, creates one of the protons loses an electron and a neutrino, but it becomes still hydrogen, but a hydrogen that's attached to a neutron now. And then, of course, there's a byproduct here of that's not a pen, of an electron and a neutrino. And this is the electron's neutrino. But it also tells you in these equations how much energy is released in this reaction. So likewise, I can have that same single proton that comes and slams into the product of this guy. If it slams into another proton, it'll turn into a helium with 2 protons and 1 neutron, and then you get a gamma ray out of it, and the energy released is 5.49 mega electron volts. And likewise, there's typically, I haven't looked in the back of this book, but typically there's several 10, 20, maybe 100, 200. Some books have thousands of these equations in the back of them. But it goes down and talks about the last result here. This is kind of in the same cycle in the sun. Sorry, every time I copy a picture, it resizes everything, even though I don't want it to. But anyway, we've got this last one. It takes 2 electrons and 4 hydrogens. They create a helium, and then 2 of the neutrinos and 6 gamma rays. And the total in that last is 26.7 mega electron volts. The interesting thing that happens here is the sun is extremely dense, and so I'm going to still, I guess, a portion of this image, the image that matters. Get out of here. We've got these bits of energy that kind of bounce around, and this sun is so dense that the energy just kind of like bounces from thing to thing, and it takes 32,000 years for that energy to be able to dissipate out to the surface of the sun and then radiate away, which is ridiculously long. It's foreverly long. I mean, not forever, it's 32,000 years, but it's a long time. But these neutrinos, we talked about these guys, they're the ones that are nearly massless. They're the ones that don't interact with very many things. And the sun is essentially just not anything to these guys, and they escape within seconds. So these guys take a few seconds, maybe about 2 seconds. But these other energies, they bounce around in there for 32,000 years before they can get up and break free of the sun. This reaction here, I erased it, and now I'm going to erase that. This reaction it's obnoxious. This reaction has a very low probability of actually happening. And ignore that last part of this thing. That's not. This has a very low probability, like very low probability of happening. Even in the sun, probability. It doesn't happen very quickly. And so this is the reason that the sun can burn for billions of years without burning out, is because this reaction doesn't just happen just because there's 2 hydrogens bouncing around each other. We still have that quantum tunneling that has to take place. It has a very low probability of occurring. And therefore, if we wanted to take this and turn it into a controlled reaction on Earth, even at the temperatures that we can create here, they don't match the sun, but so it's even in lower probability. So this is probably not a very good place to start if you're going to create a fusion reactor, but these other ones have much higher probabilities, and so this is where we would probably start. This H2 is called deuterium. There's an H3 here. It creates. This is called tritium. tritium. I don't know how to say it. Tritium. That's an M. But this guy right here is found on Earth. It's just a hydrogen that has a neutron, stuck to it, and so it's not terribly abundant, but it is about 0.015% of the natural hydrogen. So if we pick up a few gallons of salt water out of the ocean, we can harness that, we can harvest it, and actually get a supply of that. And it's not terribly hard to get, but it does have a cost associated with it that we would have to overcome and make your nuclear reactor profitable enough to cover that cost, as well as all the others. Let's see here. I'm doing on time. I'm okay. There's kind of three things that we'd have to figure out to make a controlled fusion plant on Earth. And the three keys to controlled fusion are the temperature, the density of this material, the fusible material, and time. But luckily these are complementary, meaning if you are short on temperature, all you have to do is increase the density or increase the amount of time. If you're short on the density, you just increase the temperature and or the time. So if you're short in one, the other two can come in and make up for that. But it's best if you can maximize all three simultaneously. Some terms we would have in a controlled nuclear fusion is ignition. And that is defined to be when the reactions, or when the fusion reactions produce enough energy to become self-sufficient. Self-sufficient after the external energy is cut off, or an external energy source. I'm sorry about my handwriting on this. It's been forever since I've used this, so it looks like a 2-year-old is writing this. But after that external energy source is ended or shut off. But we also have the break-even point. And that is when the output energy of the fusion reactor is equal to the amount of energy that you've put into it to get it going. And that's your break-even point. At that point, the energies have evened out, and if you can bypass that, you can then have a surplus, and hopefully at some point that surplus would pay for everything it costs to get it running from the get-go. So there's two techniques. We're not going to go into super detail on either of them because it's not actually that terribly important for us. So we'll just leave this here. We've almost got to this point. So the break-even, we're almost here, which is kind of good news. The not great news is that we can't get it to ignite. This hasn't happened. We can probably get by with, as long as we can get past the break-even point, we can always supply enough energy to keep this going. As long as we get more out of it than we have to dump into it, we can still make it profitable. But these are two hurdles, huge hurdles, and this is why you don't have fusion reactor plants providing energy on Earth is because we haven't got it down yet. We haven't figured it out. They're still working on it. They may do it. They may not. I don't know. I'm not in that field. But I wouldn't mind being in that field. All right. I think I'm going to stop here because I'm not going to be able to get through the next section in 10 minutes that the recording has. So we may end up with 3 videos of 20 minutes or so. But anyway, I'll see you for the next one. Bye.